Okay, welcome back to session 21 on plane strain. This is our third and final portion. In this portion of our session, we're going to discuss how we can use sensors to figure out what the state of stress might be at a given location on the surface of a material we're trying to analyze or a structure that we're trying to analyze. So you can imagine that this could be something that you might put on a pressure vessel, or you might put on a wall, or you might put on any type of other load-bearing structure to be able to figure out what the state of stress or what the state of strain is, and potentially also look at what the state of stress is by using appropriate relationships from material properties. So these are some examples of what we call strain gauges. They're used for measuring the state of strain on the surface of a material. And what it essentially amounts to is a wire that runs back and forth, okay? And you run some electrical current or voltage across it, or electrical current through this strain gauge. And as the gauge stretches, okay, or experiences strain, okay, the electrical resistance that we measure changes. So to kind of give a little bit of perspective on how this could be, you could kind of think of this back and forth wire as being one long bar, okay, that is being strained, or is having some force applied to it. And we know that there are a couple things that happen. One is that this bar is going to extend its length, okay? So the effective length of all of this entire wire gets a little bit longer, and the area is also going to be, if it's in tension, this bar, the cross-sectional area is going to get a little bit smaller, okay? And so we can think about the change in area, we can think about the change in length, okay? And when we think about those two parameters, we can then relate them to electrical resistance, okay? So what you have is electrical resistance here, and it's equal to the resistivity, okay, times the length divided by area. So if I make a hose longer, right, for example, I need to have more potential or more pressure, right, at one end to get the same speed, all right, of flow through it at the other end. So that's L being lengthened. If I make the cross section of the hose smaller, or the pipe smaller, right, I need to have a higher pressure to get the same amount of flow through it, okay? So this is the same kind of thing that we're dealing with, but with charges. Now, that's not the whole story in terms of what we're actually measuring, okay? If we think about the properties, the geometry, yes, and say that rho is constant, yes, we would have a gauge factor, okay, which is a ratio of the change in resistance divided by strain, that's only dependent on essentially this strain, okay, this change in length divided by initial length, and the some type of dealio with the Poisson ratio, okay. So the gauge factor, which is defined here as the ratio of change in resistance divided by strain, okay, would only be dependent on these two properties, right? What we're saying is, look, okay, if I apply a force, we have some change in the axial direction, okay, and that's going to be giving us a change in the resistance, right? So if I said delta R over R is equal to epsilon plus 2 epsilon nu, okay, so now we're seeing that this nu is coming into the change in the cross-sectional area. Okay, so it would just be these first two terms. In reality, though, there's another term, okay, and this is a piezoresistive term. Okay, so what actually happens, what actually happens is, as the material is experiencing some deformation, it can change, it has a different property called piezoresistivity that changes its resistance as it experiences the strain itself. Okay, so that's it's pretty cool. It's a pretty neat property. And so if we're considering gauge factor, it's actually important to consider all three, and this one can be the dominating one with the appropriate selection of a material. Okay. So that's one. That's kind of that's how one of these strain gauges works. And one strain gauge can give you information, right, in one direction. So if I'm just interested in the strain in the x direction, and I align my strain gauge, so I would put and make it like in the x direction this way, then that's not a bad approach. That's not a bad approach to being able to look at the the strain in that one direction. But in plane strain and in plane stress, but in plane strain, I am interested in three parameters, right? Epsilon x, epsilon y, and gamma xy. So if I want three parameters, epsilon x, epsilon y, gamma xy, I should be able to use three sensors in some configuration to be able to get those measurements. Okay, so what do? If you align them all in the same row, right, or column, you don't get any additional information. So people create what are called rosettes, where they put them at differing angles relative to each other, and then use our transformation equations to be able to determine the state of plane strain. And then you could rotate additionally if you want. Okay, so for example, if we have what we'll call this rectangular rosette, that's where we have 0, 45, 45. We can write out that and we'll call this A, B, and C, because you can calculate A, B, and C. I mean, I can say epsilon 1, epsilon 2, epsilon 3, but that may not necessarily be giving us the state of plane of say principal strains. Okay, so you can keep it in terms of epsilon A, epsilon B, epsilon C, and we can then calculate out relationships for what epsilon x, epsilon y, and tau xy, or I'm sorry, not tau xy, gamma xy will be. All right, and so this is not so bad. So this could be this, what we're doing is we're just using the epsilon x prime transformation, okay, and we're saying epsilon a in this case lines up exactly with epsilon x because theta is equal to 0. We're at 45 degrees. We plug in 45 degrees. That's 90 degrees for cosine and sine, right? And then we can come up with this expression relating the measurement on the B sensor, the B strain gauge, with epsilon x, epsilon y, and gamma xy. But now we have, right, a known and three unknowns. So we want one more sensor, and wow, this is nice. Sensor C lines up nicely with epsilon y, right? Theta is now equal to 90 degrees, okay? And so we get that epsilon c lines up with epsilon y. So now we have essentially this equation that has three unknowns, but we have two knowns here and here, okay? And so we can write out that gamma xy is equal to this expression. So given the state of strain, right, we should be able to get epsilon A, epsilon B, epsilon C, or if we measure epsilon A, epsilon B, epsilon C, we should be able to figure out what the state of strain is. Similarly, okay, we can use the same transformation equation, okay, with a different configuration. In this case, right, this B sensor, this B strain gauge, is nicely lined up with epsilon x, okay, using this equation. Strain gauge A down here is at theta equals minus 60 degrees. Okay, so we get a more complicated relationship. And like you can imagine, strain gauge C is at theta equals 60 degrees, and we get another relationship. Now these are similar. Look, this term right here, it's a minus square root of 3 over 4 and a positive square root of 3 over 4. Maybe we should add 2 and 3 to each other in order to be able to get, to knock this out and then be able to get an equation with two knowns, epsilon A and epsilon C, with two unknowns. Plus, we have our relationship that epsilon x is equal to epsilon b. So we add 2 and 3 together, and we're able to get an expression for epsilon y, okay, in terms of epsilon A and epsilon B. Okay, so this is nice. This works out nicely. Okay, right. We also use what we have here in equation 1, right, and substitute it in here. Now the most tedious part, and you guys will have to check my math, okay, is that we can figure out what gamma xy is. Okay, so we can rearrange equation 2 right here, so that we put this on the other side, and then we have our other terms here, and we plug in our expression for epsilon y, okay, over here, and then we do a little bit more algebra, and we can get that gamma xy is equal to the following. Okay, so that is a clever way, okay, to use strain gauges that I can measure in one direction to figure out the state of strain in with 3 parameters in plane strain, okay. And here's a problem for you, okay, to look at a set of strain gauges, a rosette, on a cylindrical pressure vessel. Okay, we'll say that A is in the longitudinal direction. The C rosette, or sorry, this should be the C gauge. So we have, this is A gauge, because rosette is this is the C gauge. Okay. And we're asking, what will the B gauge read? Okay, and we also are going between a state of plane stress, okay, to thinking about the general, okay, situation of what is the state of plane strain, okay, and we're going to ignore, this is one thing that we can we're going to ignore the effects of epsilon z in this case. Okay, we're going to focus more on what's happening in epsilon x and epsilon y, okay, and we're going to then use the equations that we've described for the rectangular rosette to figure out what the reading on B should be. Okay, so as a recap, we've discussed plane strain and transformations, and the difference between plane strain and plane stress, and how to use some equations to be able to figure out how to go from a given set of plane strain as epsilon x, epsilon y, and gamma xy to a new epsilon x prime, epsilon y prime, gamma x prime, y prime. And we have also discussed how to use Mohr circle to do essentially the same thing that we have with the transformation equations, similar to what we did with plane stress. And we've also discussed how to use strain gauges to be able to calculate the state of strain at a given location. So thank you for watching, and if you have questions, let me know. Have a good one.